In this video, I'm going to talk about complexation titrations, and this will mostly have to do with EDTA. So EDTA, or ethylene diamine tetraacetic acid, forms strong one-to-one complexes with many metal ions, and that's going to be an important thing to know as we go on to do calculations later on. EDTA is found in many household products, and the way it reacts with metals is to form sort of like a cage around it. So the structure of EDTA is shown down here. So here it is. It has 4 carboxylic acid groups and 2 nitrogen groups. And as it wraps itself around a metal, so the metal being this guy right in the middle here, it forms up to 6 bonds with that particular metal. So it doesn't always form 6, but a lot of the time it does. And because of that, it's a really strong complex, right? Forming 6 bonds with one single metal atom. And the equilibrium of the reaction between the EDTA and the metal is given by a Kf value, or a formation constant. Now, if you look at those two arrows, notice that the top arrow, the one that's pointing towards the products, is much larger than the one pointing back towards the reactants. That's just indicating that this is a very product-favored reaction, meaning that there will be mostly that EDTA metal complex in solution and very little free metal ions and free EDTA. So EDTA, when it binds to a metal, it's called a ligand. And a ligand is an atom or group of atoms that are bound to whatever atom you're interested in. So in this case, we are interested in the metal, so the ligand is EDTA, but the ligand could also be something like humic acid, which is a naturally occurring organic compound that can also make complexes with metals. So if the ligand binds to a metal through one atom, it's called monodentate. Mono meaning one, dentate meaning tooth. Now EDTA is a multidentate ligand because it can bind to the metal through more than one atom. And since EDTA commonly bonds to metals with 6 bonds, that would make it hexadentate. So 6-toothed, or this question mark here would be a 6. Another way to refer to EDTA or other ligands that will bind to metals or other atoms of interest are called chelating ligands, and it's from the Greek word meaning claw. So basically it describes how that particular ligand interacts with the metal. So it kind of grabs onto it and surrounds it, kind of like a claw from a lobster or a crab might do. Now, transition metals typically bind 6 ligand atoms, but a lot of ligands like EDTA can bind 2 metals with more than one bond itself. So ATP is another important tetradentate ligand in biology. So that means it can bond to metals using 4 different bonds. So in this case, if you look on the right, the metal ion is here right in the middle, and it is bonded to the ATP through 4 different bonds. So ATP is tetradentate, EDTA is hexadentate. The important thing to know about these ligands is that the stoichiometry is 1-to-1. This is especially important for EDTA, meaning that one EDTA always bonds with one metal. Even though it binds with 6 different bonds, it's still a 1-to-1 mole ratio, or a 1-to-1 stoichiometry. So this slide just shows a couple other ligands that do the same type of thing as EDTA. Now, most of the time, this is a strong complex when they form the metal ion complex. So there's the EDTA that's bonding to the metals. Usually that's a really strong complex, but it's not very strong for sodium, potassium, or lithium. So every other metal, it's a strong complex. For those 3, it's not nearly as strong. So just quickly, what do we use chelating agents for besides EDTA titrations in the lab? So there's the copper EDTA titration. We could also do a hard water titration that uses EDTA to react with the magnesium and the calcium in the water. EDTA is also used in water conditioning agents, such as for aquariums, to make sure that any toxic metals that are in the tap water are chelated with the EDTA, and once they're chelated, then they are not available to be incorporated into the cells of the fish. And there's also chelation therapy, which can be used to treat specific genetic defects. So one example of chelation therapy is one that clears excess iron from patients' bloodstreams. So it uses a ligand to react with the iron, which then clears it from the patient's bloodstream. So without any therapy, without any intervention, this disease can result in death before the age of 10. If there's just blood transfusions, then that can extend a person's life to 25 and beyond, but most people won't live quite that long. But with this transfusion and this chelation therapy, patients will live quite a bit longer and lead a mostly normal life. So as I was saying before, EDTA chelates almost everything. And the complexes that are formed have what are called formation constants, or Kf values. And the higher the formation constant, the more readily the complex forms, or the stronger that complex is, or the more stable that complex is. For EDTA, pH is also important. So EDTA will react with different metals at different pH values. So when you did the copper EDTA experiment, you did have to use a buffer, and that made sure that the pH was correct for EDTA to react with copper. So another reason why pH is important is because some metals, if the pH is too high, they will form metal hydroxides. And if they form hydroxides, they will no longer be able to be accessed by the EDTA. And if the pH is too low, then H plus will compete with the metals for EDTA. So the pH has to be correct in order for EDTA to do its complexing with the metal. And the pH range determines what metals EDTA complexes with. So here's just a list of formation constants, and I want to bring your attention to just a few here. So the first three, lithium, sodium, and potassium, notice that their log Kf value is really low compared to the rest of them. So the greater that log K value is, the stronger the complex is going to be, or the more stable the EDTA metal complex will be. So as I was saying before, EDTA doesn't make strong complexes with lithium, sodium, or potassium. But if you look at all the other metals in this table, particularly some, like gadolinium or bismuth or thallium or cobalt, for example, those are going to make very strong EDTA complexes. So as stated on a previous slide, EDTA is a weak acid. So each of the ionizable protons has its own pKa value, and they're all listed here. So we have a pKa 1 of 0 for one of the carboxylic acids, 2 for another one, 1.5, 2.69, and the other two, right in the middle, the NH pluses, has pKa's of 6.13 and one of 10.37. So the pH is going to determine what form of EDTA is present in solution. Is it fully protonated? Is it somewhere in the middle where a couple of hydrogens have been lost and a couple of hydrogens still exist? Or is it fully deprotonated where all of the hydrogens have been ionized? So in this slide, I've just zoomed up on a table here that shows you what pH values EDTA works at for specific metals. And I've zoomed up on magnesium and calcium because those are components of hard water. And I've also zoomed up on lead because that is something that's also present in water, or could be present in water, hopefully not, because it's quite toxic and can cause health issues. But if it is present and we just want to measure the magnesium and calcium, we can choose a particular pH such that the lead is going to precipitate, whereas the magnesium and calcium will still be in solution. So the little letters underneath each of those bars are just a type of indicator that would be used, and the bars themselves represent the pH range over which EDTA will react with that particular metal. So magnesium and calcium, you can see they both react with EDTA somewhere around pH 10. But for lead, this dark part of the bar means that at that particular pH, we would need something called an auxiliary complexing agent to prevent the formation of lead hydroxides. But if we're only measuring calcium magnesium, we don't care if lead hydroxides are formed because we would not want to measure lead in this case. So the formation of lead hydroxides just means that the lead hydroxide will precipitate, and only the metals that are in solution will be available for the EDTA to react with. So now let's talk a little bit about titrations. So when we're doing a pH titration, we know we use a pH indicator, and the indicator itself is a weak acid or a weak base, depending on which form it is. And they work because when you're doing the titration, when the titrant is added, it's also reacting with the indicator to allow it to change color. Now for metal ion indicators, they work a little bit differently. So metal ion indicators will create a complex with the metal itself initially. So we have, in this case, magnesium ion, the ion meaning the indicator. So that particular complex, in this case, creates a pinkish color, kind of a wine red color. And if we add EDTA to it, since EDTA makes strong complexes with magnesium, it's going to preferentially bind to the magnesium, so making this magnesium EDTA complex, and then it will liberate the indicator, and indicator that is not bound to the magnesium is, in this case, going to be a blue color. So you can tell when this particular titration is done when the solution turns to a bluish color. Now, we've talked about back titrations before, and I'll have an example of that a little bit later on. So sometimes they're useful for EDTA titrations as well. So it's the same process as we talked about before, where in this case you'd add an excess amount of EDTA. So previously in an acid-base titration, you'd add an excess amount of the strong acid or strong base, whatever the titrant is. In this case, the titrant is EDTA, so we add an excess amount of EDTA. And then since we passed the endpoint, there's a certain amount of EDTA that was needed to get to the endpoint, and then we've added excess EDTA after the endpoint. So now we have to figure out how much excess EDTA we've added, and in order to do that, we would use a standard solution of, say, magnesium or some other metal to react with that excess EDTA and bring us back to the endpoint. Now, in the case of these types of complexation titrations, some metals are good at what's called blocking the indicator, which basically means that they will create relatively strong complexes with the indicator. And in order to force that reaction towards making a metal EDTA complex, adding excess EDTA is going to help that happen. So that's when using a back titration for a complexation titration is useful. So this slide just shows you the colors of copper solutions with different ligands. So the first one we have is copper sulfate, so that's just the same one that you use in lab when you initially mix up the copper solution, so it's kind of a light blue color. If you add some ammonia to that, some NH3, the ammonia will displace the sulfate to create a copper NH3 complex, and that is a dark blue color. And then if we titrate it with EDTA, which is what you have done or will do in lab, you notice that the color, at least from the first copper sulfate color, the light blue gets a little bit darker. So the copper EDTA complex is a little bit of a darker blue than the copper sulfate complex. So now we'll just quickly talk about a few of the titration techniques for EDTA. We've already talked about direct titration and back titration for pH titrations, and it's the same process for EDTA titrations, but the steps are a little bit different because we need a buffer in this case to make sure that the EDTA will react with the metal. So for a direct titration, we'll have a buffered analyte and we titrate it with standard EDTA. So again, this is just like the copper EDTA experiment, and the indicator is going to change color at the endpoint. Now, we didn't use an indicator in the copper EDTA experiment, but if we were to do a hard water experiment, we would use an indicator, and that indicator would change color from a wine red to a light blue color at the endpoint. And depending on what other metals were in solution, we might have to use something like an auxiliary complexing agent, which would form a complex with the metal that we're interested in and make sure it doesn't precipitate at a particular pH that we are working at. So back titration, just the same process as I talked about in the previous slide. Now we also have what are called displacement titrations and an indirect titration. So displacement titration is useful if there is no satisfactory indicator. So if we don't have an indicator that will change color at the endpoint, we can do what's called a displacement titration. So we'll treat it with excess magnesium EDTA, for example. The magnesium is displaced by the analyte because magnesium doesn't create a really strong complex with EDTA. I mean, it's stronger than lithium, potassium, and sodium, but when compared to the rest of the metal ions, it's pretty weak. So what we're trying to do here is displace the magnesium from the EDTA by replacing it with the analyte. So the analyte is going to create a stronger complex with EDTA. And now, since we have magnesium in the solution, we can titrate that with the standard EDTA and use an indicator that is useful for magnesium titrations. So an indirect titration is used to determine concentrations of anions in solution. So EDTA itself is only good for cations. Okay, it's not going to bind to anions, but if we wanted to find the concentration of anions, then we would do what's called an indirect titration, and we might do something that is outlined in these particular steps here. But in the end, we'd figure out the concentration of sulfate instead of the concentration of, say, barium in this case. Another thing to consider when doing these titrations is that we may have to protect some component of the analyte from reacting with EDTA. So these are called masking agents. So if we were to, say, measure the amount of calcium in milk, there's a whole bunch of other things in milk that will react with EDTA. There's iron 2+, iron 3+, zinc, copper. So what we can do is mask the iron, the zinc, and the copper with the cyanide anion. That'll create iron cyanide, zinc cyanide, and copper cyanide. And basically that will prevent those particular metals from reacting with the EDTA. So it'll only leave the calcium, and if the calcium is only available to react with EDTA, then we will be measuring only the calcium. So one thing that may or may not be becoming clear right now is that EDTA just reacts with whatever metals are in the solution. So it's not very specific, it's not very selective. So if we want to be selective for a specific metal, then we have to do some sample preparation to make sure that those particular metals that we're not interested in will not react with EDTA. So we do things like adding masking agents, or we use a specific pH. Okay, so just using EDTA itself is not going to give us a concentration of a single metal cation. We have to make sure that the conditions are correct for the EDTA to react with the metal, and we have to make sure that other metals that will also react with EDTA are made unavailable by using a masking agent. EDTA titration curves look just the same as any old pH titration curve. There are three regions: before the equivalence point, at the equivalence point, and after the equivalence point. Before the equivalence point, we have excess analyte, or excess metal N+, whatever it might be, 2+, 3+, and that is after some EDTA has been consumed. Okay, so we add a little bit of EDTA, but we haven't added enough yet to get to the equivalence point, so there's still lots of that metal left in solution. At the equivalence point, we've added enough EDTA to react with all the metal. So at this point, there's very little metal in the solution itself, and since EDTA creates a really strong complex with metals, the EDTA metal complex isn't going to dissociate much either. So the EDTA is going to hang on to most of that metal, and only a little tiny bit is going to be released from the EDTA. Now after the equivalence point, we've added excess EDTA to the solution, so that's going to eat up even more of that small amount of metal that is remaining in solution from the equilibrium between EDTA and the EDTA metal complex. So at this point, there's almost no metal in solution, almost no free metal, and it's almost all complexed to the EDTA. So here's a picture of a couple of titration curves. Notice they look exactly the same as a strong acid, strong base titration curve. The difference is we have volume of EDTA on the bottom rather than volume of strong acid or volume of strong base. And on the y-axis, we have PM. Which is just like pH. pH is the negative log of the concentration of H+. PM is the negative log of the concentration of metal. So you can just consider this being another way to express the concentration of the metal. If we have a number that is low, we're going to have a large amount of metal. And if we have a number that is high, a large PM, then we have a very small amount of metal in the solution. So notice in these two titration curves, they start off identically, but they end up at slightly different spots on the titration curve. So the equivalence points are a little bit different for magnesium and for calcium, and the amount of metal that's in solution after the equivalence point is a little bit different in each of those situations as well. And the steeper that curve is, the stronger the complex is. So the calcium EDTA complex is stronger than the magnesium EDTA complex in this case. So here's just another example using magnesium and zinc. Again, you can see that there's quite a difference in where they end up. The zinc curve is much steeper than the magnesium curve. So the zinc complex, zinc EDTA, is going to create a much stronger complex than magnesium EDTA. And you can see that by their Kf values. So zinc EDTA has a Kf value of 3.2 times 10 to the 16, whereas magnesium EDTA is 6.2 times 10 to the 8. So the zinc EDTA complex is 8 orders of magnitude stronger than the magnesium EDTA complex. So let's just go over a quick example of a back titration. So nickel 2 plus was back titrated with standard zinc 2 plus at pH 5.5 using xylenol orange as the indicator. The unknown solution containing 25 milliliters of nickel 2 plus was first treated with 25 milliliters of sodium EDTA salt, resulting in a yellow color upon addition of the indicator. The solution was then back titrated with 17.61 milliliters of zinc 2 plus to the red endpoint, and we're asked to determine the concentration of nickel in the original unknown. So the steps to do this are exactly the same as they were to do for a back titration using an acid base. Okay, so the first thing we have to do is figure out how much EDTA was added. So remember, we're adding EDTA past the endpoint. So a certain amount of the EDTA will be used to get to the endpoint, but we're adding extra. So we're going to add some excess EDTA. So we'll first figure out the moles of EDTA that were added, and we can use this information here. So we have the volume of EDTA and the concentration of EDTA that were used. And if we do the calculation, 25 times the concentration, we get 1.321 millimoles. Now the next step is to determine how much of that EDTA is in excess. And for that step, we just need to know how much zinc we added. So we do the same process that we just did. We're trying to figure out how much zinc was added, so we use those two numbers there. So we'll call this excess EDTA, and if we do that calculation, we get 0.4049 millimoles. Now to determine how much EDTA was needed to get to the endpoint, we simply subtract the excess EDTA from the moles of EDTA that were added. So the moles of EDTA to get to the endpoint ends up being 0.9161 millimoles. Now to turn this into nickel, we must realize that the nickel and the EDTA react in a 1-to-1 stoichiometric ratio. So the moles of EDTA that were needed to get to the endpoint are the same as the moles of nickel that were in the solution. Now that we have the moles of nickel, we also have a volume of nickel that was initially used, which was 25 milliliters. So taking the moles divided by the liters is going to give us the concentration of nickel in this unknown solution. And that equals 0.03664 molar. So now let's do a couple examples where we will predict what the predominant EDTA species would be at a particular pH. So this is very similar to what we did in previous chapters where we had a triprotic acid or something, and we were asked what form would this be in at a particular pH. Now the only difference here is we have 6 particular forms of EDTA, and we have to decide which form it's going to be in. So each of the pKa's are listed on the right, and using these little box diagrams I find fairly intuitive for determining at what pH a specific form of a acid or base or whatever would be present. So if we just list from left to right the different forms of EDTA, okay, so we have the 2 plus, the 1 plus, the neutral, and then the various anions of EDTA. And we're asked, what is the predominant species at pH 5? So the way these diagrams work is each line, like this line, this line, and this line, for example, all these represent pKa values. So if the pH were at exactly, say, 1.5, which is one of the pKa values, pKa2 in particular, that means we have equal amounts of both these guys, okay, because we're right in the middle of them. So we have equal amounts of H5Y plus and H4Y. Now we're asked what is the predominant species at pH 5. So the easiest way to figure out where we are on this diagram is to fill in the rest of the pKa's. So the next pKa will be 2, the one after that will be 2.66, and the one after that 6.16. So at pH 5, we know we're between these two values, so the predominant species is going to be this one right here. So the answer is going to be C. In this question, we're asked what the pH would be when there is an equal amount of HY3 minus and H2Y2 minus. So we're looking at this compound here and this compound here. So we know that there will be equal amounts of it when the pH is equal to the pKa, which is this guy right here. And the pKa for that one ends up being 6.16. So the answer for that one is going to be B. Okay, last one. What would the pH of an EDTA solution be at each of the following arrows? And what is the significance of each arrow? So I've already mentioned that the significance of the arrows at these particular points is where the pH equals the pKa. Okay, so that's the significance of those arrows, and the significance of the other arrows is just that the predominant species will be the one that it's pointed at. So we can fill out the pKa's pretty easily. So again, this is going to be 0, 1.5, 2, 2.66, 6.16, and 10.24. And the ones in the middle, they would just be halfway in between each of those pKa values that we've listed. So we'd have like 0.75, 1.75, and so on and so forth. So a quick summary of titrations. We've done acid-base titrations. We've seen the difference between strong acid, strong base titrations, and, for example, strong acid, weak base titrations. We know there's a buffering region in weak acid, strong base, or weak base, strong acid titrations. There is no buffer if it's strong acid, strong base titrations. We use pH indicators, and they change color because they are also being titrated, and will change color based on their acidic or basic form. And the concentration of H plus is going to determine the pH. For EDTA titrations, they're used for determining concentrations of metals, and we use a metal ion indicator to determine the endpoint. And remember, the indicator works by first complexing to the metal itself, and that'll have a specific color. But then when EDTA is added, the EDTA displaces the indicator, so it will create the EDTA metal complex, and then the indicator will be just free in solution, no longer complex to the metal, and then it will have a different color. So when all the indicator has been removed from the metal, then the color of the solution will have finished changing. And again, the important thing about EDTA titrations is that metals and EDTA form 1-to-1 complexes. 1 mole of metal reacts with 1 mole of EDTA. Okay, so that's all I have for this. If you have any questions, please let me know.